So it is a pleasure to introduce now Javier Gargiulo from UFF. He's going to talk about logarithmic varieties, the geometry of varieties of logarithmic Pfaff equations.
Okay, it's okay? Right. Thank you, Ariel, for the introduction. Thank you to the organizers for giving me the possibility of this talk. It's a really pleasure to be making a talk here at IMPA. So I will try to make a sort of self-contained talk about foliations, but I will try to keep everything as much basic in terms of algebraic objects as much as I can. Okay? So I will start just with some notation. Let me fit some notation and very basic notation and definitions. Notations and definitions. I will also take advantage of the talk of Sebastian where he introduced most of the objects that I'm going to use. But in my case, everything is going to fix. The field is going to be the complex numbers, and the variety always is going to be the projective space. Okay, so let me use this notation Sn to the ring of polynomials in n+1 variables. This is graded, typically graded, a graded ring, just by the homogeneity of the polynomials. And also I can identify these homogeneous polynomials as the global sections of the d power of the hyperplane bundle on Pn. And I'm going to use this notation we can fix Q here. It's just the Kähler differentials over this ring, or you can also interpret this like the global sections of the sheaf of differential forms over the affine space. And this is also a graded ring. This is graded by the total degree of the corresponding differential form, like this. And in terms of a projective object, I am gonna, well, we can say is that the global sections of the twisted differential forms in the projective space by the line bundle OD, this corresponds exactly to homogeneous differential forms of total degree D, satisfying that the inner contraction by the radial Euler field is equal to 0. So all the directions that are radial in some sense the form needs to be constant, okay? So I just want to say that when Q equals to 1, an element here for me, an homogeneous or a projective homogeneous differential one form on Pn of total degree D, for me it's going to be an algebraic Pfaff equation on Pn of degree D. Okay, this is for me an algebraic Pfaff equation. Okay, so I'm gonna fit in this sense two sets. We can think on all the projective or all the Pfaff equations here that satisfies the integrability, the so-called Frobenius integrability condition here. This imposes some quadratic equations on the coefficients of the homogeneous form. Okay, and I'm going to use this calligraphic notation. Well, let me fit here D. Okay, I'm going to use this calligraphic notation to say just to keep projective classes of these objects. Okay, so these are the projectivization of this set in some sense. Okay, satisfying the Frobenius integrability condition. Okay, so this more or less lives on a projective space whose dimension depend on n and d. Okay? So if we write everything in homogeneous coordinates like this, another thing that is important is a singular set that Sebastian talked a lot about it. So the singular set of the corresponding Pfaff equation is just the zero locus of all the coefficients of the differential form. Zero locus of this. And I'm going to use a separate notation to denote the irreducible ones. I mean, I'm going to use UND to denote all the elements here, all the elements in this space of integrable Pfaff equations like this, satisfying that its coefficients, the greatest common divisor between its coefficients is equal to 1. So these are the integrable Pfaff equations, and these are the irreducible ones. Here, irreducible means, in particular, that so omega irreducible implies that the codimension of the singular set is greater or equal than 2. So in case that you have an element here, is what is called a foliation for us, because we are fixing the degree, another geometric invariant of this object, which is the degree of the corresponding foliation. These elements here induce singular projective foliations on Pn of a fixed degree. So if I mean an element here, it's a foliation, and when I talk an element here, I'm going to say Pfaff equation. Okay? So here I'm allowing, in some sense, singularities in codimension 1. So, 2.
Is this related to having content?
What? See, it's equivalent to if you can write this form as a product of a polynomial and something. Irreducible means in that sense. Being irreducible is that you cannot factorize this omega as a product of a polynomial and a lower graded form. Okay, so let me fix now. Let me fix this degree D, greater or equal than 2, and an M lower or equal than D. So I'm going to denote PMD, all the partitions of this number into M parts. So I'm going to fix vectors of integer numbers or natural numbers, M natural numbers satisfying that its sum equals to D. This is for me a partition of D into M parts. Okay. What?
1 plus 2 is different from 2 plus 1.
So
The partition 1, 2 is different from the partition 2.
yeah, at the beginning, yes. Yes, are order partitions, ordered by this.
You want the idea to be positive or
Yeah, I'm going to fix all of them positive. Okay? And definition, a differential form like this. Let's say it's homogeneous of degree D, is logarithmic of type D. If omega can be right like this. But at least at the beginning it's just a combination of usual logarithmic derivatives like this. But in order to obtain an homogeneous differential form, I'm going to add here the product of all the denominators that appear here. Okay, so it's a classical differential logarithmic forms in the usual terms of differential geometry. In fact, this corresponds to the global section of the sheaf of differential forms using the divisor of these polynomials fi. But just if you don't want to think in that terms, it's just something that you can write like this, where the lambda i's, sorry? The lambda i's here are just complex numbers, and the polynomials fi are homogeneous polynomials of degree di. This is the type. So that's the definition. It's logarithmic of type D, which you can write like this. But something very easy to check is that all these things are integrable. This is very easy to check because this one that appears here is closed. So it's very easy to show that this is integrable. And in fact, it defines a projective differential form. I mean, the inner contraction by the radial field equals to 0 if and only if the lambda i's satisfies this hyperplane condition with respect to the degrees. So it's natural to define the space of the hyperplane induced by this degree di's as just all the coefficients lambda satisfying that condition. Now, using this type of logarithmic forms, you can produce elements on these spaces, this and this. Just consider all the, logarithmic, L like this. All the forms here, integrable differential forms, such that omega is logarithmic of type D. Collect all the logarithmic forms of a certain type. This produces an element, a variety here. And projectivizing this object, you can obtain, if you take the projectivization of this object, if you take the projectivization of this object, you produce something here. Okay? Well, a first theorem here, this is not new. A theorem originally proved by Omegar, Calvo, Andrade. Says that this variety is here for a fixed type. For a fixed type, this variety here is an irreducible component. Of this variety. Sorry?
That's not the fully reducible component. You have higher order codes.
If you consider, well, I mean, yeah. If you consider the intersection with irreducible ones, this is an irreducible component of this. That's what we mean?
There are things which are not logarithmic in the closure of this.
Ah, okay.
It's an open set of an irreducible component.
Yeah, of course. Writing like this, you're right. Of this space. Okay. And after some years, in a result with Kuckerman and Cesar Mathry, without some more information about this, we reprove this result, and we also add the condition that this thing, this scheme, or this variety that appears here, is generically reduced along the logarithmic, this sort of logarithmic component. Sorry? Yeah. Here, for the people not from algebraic geometry, generically reduced means that this condition here, the integrability conditions, impose an schematic structure on the variety. And reduced means that, in some source, it's a version of being smooth. Okay? Just to keep an idea in mind. Yeah, there are several components. One huge problem to understand are all the reducible components of this variety. Try to classify all the reducible components. I'm just pointing out some of them constructed like this, okay? So there are many works trying to classify all these irreducible components. But now my motivation is another. So the motivation for this recent work is not posted on archive yet. Our motivation is the following, is to understand the geometry of this variety, okay? That's the original motivation, understand the geometry of these logarithmic varieties. Well, understand something means something very huge, very general, but I mean, at the beginning we are very focused on trying to understand the degree. The degree means that this naturally lives in a projective space, so try to compute the degree as a projective variety. And then the work, this is very hard to do, and we focus more or less on the singularities, and a study of the singularities that can appear here. Okay, so who is connected, sorry? The calligraphic one is connected but has a lot of irreducible components. So you have the decomposition of certain variety. So here you have, if you look at the coefficients of the differential form, it's very easy to compute. These conditions here are quadratic equations here. If you look at this, in this space, in this open space, this condition of having singularities of codimension greater or equal than 2 is an open condition on the coefficients. And the integrability condition are a lot of quadratic equations on the coefficient of this. This defines a scheme, just like this. And they have some irreducible component with certain scheme structure. So in the generic point of these things that I define here, there are no schematic, there's nothing schematic playing in these things, okay? So maybe another more natural or serious introduction to this subject is to consider the following parametrization, okay? Maybe it's something more clear if we define the following. Consider the map mu that consider the coefficients lambda that I defined there and a product of spaces of homogeneous polynomials and goes through this variety of integrable equations. Take the coefficients lambda here and the polynomials fi here and just write this formula. This is a multilinear map. And you can projectivize everything from here and obtain a rational map here, from here to the product of these projective spaces of homogeneous polynomials of fixed degrees and goes through here. This turns to be now a rational maps because when this formula equals to 0, this is not well defined. And what Georgie says 1 minute ago is that what I want to define is that the logarithmic variety that I define here is the Zariski closure of the image of this map. In the generic point, is something that you can write like this, but appear some things in the closure, in the Zariski closure. So here it's very clear. This is the object, okay? You want to understand things about the degree of this object, the degree of the image of a rational map, okay? And you want to understand singularities of these things. In particular, you could think on singularities of this map, or just multiple points of this map, and so on, okay? So the step 0 for everything is to understand the base locus of this map. So what things are on the base locus? Where it's just consider the preimage by 0 of this set. These are the points where this formula the points where this formula vanishes. In this point, this map is not well defined. Okay? So the base locus of the parametrization rho, so this is a rational map, right? And the base locus of the rational map are all the points avoiding the, all the irrelevant locus that appear in these projective spaces. This base locus is exactly the projectivization of this, erasing some irrelevant locus. This is what the base locus of this map. So, let me describe how is this base locus, how complicated is this base locus. So, let me begin with some lemma, which is the key to understand the base locus of the parametrization. So, select coefficients lambda I and polynomial fi. I'm trying to understand when this formula is equal to 0. At the beginning, it's not so clear how to produce something that it's 0. So let me show a lemma of Janeiro, which is the key to understand everything. I always forgot how to write Janeiro. So if you consider G1 to Gk irreducible polynomials, just irreducible polynomials needs not to be homogeneous and distinct. Sorry, something that I don't say is that this being 0 is equivalent to this being 0. If you divide by the product of all the polynomials fi are the same. So in this case, this equals to 0 implies that all the coefficients are equal to 0. So if the polynomials are irreducible, you don't have any chance to produce something like this. This is trivial. So this is the key to understand how to produce an example. Consider polynomials that are not irreducible. So this is in fact what happened. Consider the fi, the composition of the fi as a product of certain irreducible polynomials. So here I'm going to select n prime irreducible polynomials and distinct. And the powers that appear here, maybe some of them could be equal to 0. So I collect all the irreducible polynomials that appear in all the fi. Okay? And then it's very easy, and very easy computation is just the logarithmic derivative to see that this expression is the derivative of calculus, showing that this equals to this. This is the logarithmic derivative, and this turns to be this. So sum lambda I e j like this. And Janeau's lemma implies that the coefficients needs to be, so this is 0 only when the coefficients lambda times this matrix of powers that appear in the decomposition is equal to 0. So here is the key to understand the base locus. So more notation. More notation here. And if you consider a partition, an original partition of D, for an element here, and for something here, a vector partition of D bar is just a selection of a matrix and another vector such that E times D9 prime equals to this. This is a vector partition of the vector. I mean, a combination of the columns of E is a decomposition of this vector. It's a partition of this vector. So I'm going to use a notation for here, for this, like this. This is a partition into m prime parts of the vector D. Okay? It will be also useful to keep in mind the rank of this matrix that appear here. So I'm going to fix another number k here, just to say that these are partitions. I'm going to fix partitions here, such that the rank of the matrix equals to k. Why to fix the rank? Because it's the condition that appears here. So I'm going to define the linear variety induced by the matrix just as all the vectors lambda, such that lambda times E equals to 0. So this is this condition that appears here. And in such case, this is a set, this is a linear space of codimension K. Okay? So in particular, were all these things for a given partition. You can also define a notion of subpartitions of this. So phi1 given by a matrix and a vector like this is a subpartition of phi2 given by another matrix. One element is a subpartition of the other. If there exists another matrix, if we satisfying that, let me write clear because I always get confused with the where are the products. E2 is equal to E1, E3, and E3 sends D2 to D1. This is a subpartition. There's a natural notion of subvector partition. Okay? So this is everything that I need. And the thing here is the following. If you consider a partition, a vector partition of the original vector, you can consider the following Segre-Veronese map given by this. The Segre-Veronese map induced by this partition is the following. You go from the product of the polynomials like this to the product of the polynomials like this. And you send the polynomials, certain polynomials Gj to the product of the Gj to the power induced by the coefficients of the matrix. Okay? This is exactly what appears here. Okay? This is the Segre-Veronese map that appears here. And using this, with all this notation, that trivial remark that I made there turns to be the following. If you consider B sub phi for every partition, right? For every partition into m prime parts of the vector D, if you consider B phi to be the space induced by this linear space induced by the matrix times the image of this Segre-Veronese map, this is contained in the zero locus of the multilinear map. This is, a more sophisticated way to say this. Okay? So, theorem. This turns to be the base locus, exactly the base locus. So, A, the zero locus of the multilinear map coincide exactly with the irrelevant locus coming from all that projective spaces that appear in the domain. And the union, let me write clear, going from k equals to 1 to m minus 1, and the union of all phis given by vector partitions of the vector D using matrices of rank k of these varieties B sub phi. All the possible ranks that appear in the matrix came from k equals to 1 to n minus 1. Okay, recall that D is a partition. It's also a partition into m parts of D. So these are the ranks that could appear if you consider a matrix of higher rank are all in the relevant locus here. So this is a decomposition. These are all closed varieties that decompose the zero locus of mu. And another interesting thing is that trying to think on the irreducible components that appear here, two of these varieties satisfies an inclusion. So B sub phi 2 is included in B sub phi 1. When there are inclusions among these closed sets, well, if and only if one partitions, vector partitions, is a subvector partition of the other. So it's a very algebraic approach to understand this. And also the rank of the matrix E2 needs to be the rank of the matrix E1. The rank is fixed. So this says, as a corollary, says that the irreducible components of the base locus of the parametrization, the irreducible components of the base locus of the parametrization are in correspondence with all the varieties, all the projectivization of these varieties, where this phi needs to be a maximal element of this set of vector partition functions of the vector D, considering the order that I defined before, varying the rank from 1 to n minus 1. These are the irreducible components of the base locus. So it's not hard to understand the base locus of the parametrization here, but in order to understand the degree, it would be great to solve this map in some sense, you know. This is a rational map. In order to understand the degree, a classical intersection theory approach says that you need to, in some sense, consider resolution of this rational map and try to understand the preimage of the hyperplane section when you resolve. Okay, it's a classical approach. So what's the problem here? You understand the base locus. The base locus here is something very easy to, or the irreducible components are something very easy to describe. But the problem is that everything I say here in the right hand is everything set theoretical. So if you consider the coordinates of rho here, this imposes a schematic structure on these components of the base locus. So in general, these things are not reduced. You cannot consider just the blow-ups with centers in these things and resolve. So this in general could be, well, no, let me say, is typically non-reduced. So it's not so easy to consider a solution of this map. In fact, we have a result to understand when it's reduced in terms of numerical things on the partition thing. We know how, which of these varieties are reduced and which are not reduced. In general, are not reduced. Okay, so let me show also an example. Let me show how is the time. So let me show an example.
The principle might also be that the smaller is unaffected component of the bigger, or this is...
The smaller one of these?
Yes, you're saying that the maximal loss I give you a component.
Yeah.
So it's also possible that the smaller one gives you some embedded component, so some non-reduced.
Yeah. So this also happens. For each rank, there are maximal elements of this set. From k equals to 1 there are only one maximal element. In any other cases, there are various maximals. You can describe everything in more combinatorial terms, but it's not so easy. In general, most of them have embedded components, or a structure of a scheme which is not reduced. Okay, so example. When the vector of degrees are all equals to 1, we are going to say that it's logarithmic of linear type. Because all the polynomials that are involved are homogeneous of degree 1. Okay? And the components of the base locus in this case, so the maximal elements here, in this case, are more easy to describe. Maximal elements are in correspondence to this set, are in correspondence to, like this, partitions of the set 1D into k-parts. These are exactly the maximal elements in this introduction. So the union of all the sigma i's is the set 1D. And here, again, k varies from 1 to d minus 1. And for a partition like this, for a partition like this, the corresponding component in the base locus is very easy to describe. It's just consider lambdas and polynomials f with the following condition. Are just diagonals on the f induced by the partition set that appear here when E and J are on the same part of the partition. You consider these diagonals. And the coefficients lambda sums 0 in every part. And these are the reducible components of the base locus in that case. So in this linear case are more easy to describe, and you have more chance to give an approach to this. So at that point, we turn to study that linear case because of that. So in that case appear this variety of Pfaff equations of linear type. So in this case, you have the following. Let me write everything again. You have, so here the vector is D. It's just fixed D once. And the parametrization is just this. Is the projectivization of this hyperplane equation, and appears D copies of the space of homogeneous polynomials of degree 1, and you have a rational map here going to the logarithmic variety inside this. Okay? So in this case, the base locus more or less is checked in some sense. Okay. And another thing that you can consider in this case is something related to the first question at the beginning of the talk, is the chance of interchange here, the coefficients. So in fact, you can here act by the action of the symmetric permutations. So you can consider, you can permute on the indexes of the coefficients lambda and the polynomials f, and defines the same logarithmic form. Here are all of the same degree, so you can quotient by the action of this permutation group. So the current work with Fernando was to trying to understand now the geometry of this in this case, of the variety on this case. So our motivation was to understand three things. These are not in the order that we thought and we write, but it's in the order that I'm going to try to explain. So the first is to understand, so let me say something, which I didn't say yet, is that this map, in this case, quotient by the action of this symmetric group, this map is generically injective. So this map, rho, is generically injective. Okay, so there is an open set where this map is injective, okay? So in order to understand the singularities and the degree of the image of this map, we started with the multiple points of this parametrization. These are a sort of alpha singularities in some sense of the variety, which is the image, just to give a picture in mind. Then the singularities of the map rho, a sort of cuspidal type singularities. I mean, the points where the derivative of Zariski derivative of this map has kernel of dimension greater or equal than 1. And in that case, was very interesting to compute. We could compute something that is called the Tom Borman stratification of the singular set. So, and then another thing that we want to understand was to understand the arrangement of the intersection of the components, of the schematic intersection of the components of the base locus. Understand this schematic arrangement of all the components of the base locus. Okay, that was trying to understand a possible resolution of the map. Because of the time, I'm going to have time to describe one of the three. I select this one because this and this are a lot of computation, and maybe it's only interesting maybe the result, but not more or less the techniques that are behind. But here that's something very nice to understand, so, well, to see. So how to produce multiple points or alphas or triple points or things like this in the logarithmic variety. So definition. Let's fix a logarithmic Pfaff equation is just an L multiple point, just if the cardinality of the preimage by rho is just L. This is an L multiple point. So how could this happen? Well, in order to describe this, I need to recall some things about algebraic solutions. So let me recall some things about algebraic solutions of Pfaff equation. So a polynomial H, homogeneous of degree E, is an algebraic solution of omega if H divides omega wedge dH. This is the definition of being an algebraic solution. A rational homogeneous expression like this, where f and g are homogeneous polynomials of the same degree, and maybe we can assume coprime. It's a rational first integral. Let's say rational first integral if dr wedge omega equals to 0. These are two basic definitions about algebraic solutions of Pfaff equations. And in fact, when a form has a rational first integral in this sense, the form omega, the algebraic Pfaff equation, is integrable and is algebraically integrable in terms of the pencil that appear here. So let me say this. If R equals to f over g is a rational first integral and H is an algebraic solution, then, well, let's say that this algebraic solution is irreducible. an irreducible polynomial, then H divides one of the fibers of the pencil induced by the rational first integral. So all the fibers of the pencil Fj, all the fibers of this pencil contains the information of the algebraic solutions of the form. And another very interesting thing is that if Rf over G is a rational first integral and omega is irreducible, there are also a very particular expression for omega. I mean, if you compute G df minus f dg, this is a constant and a product of certain polynomials hi, mi minus 1, omega. So there is a way to compare this sort of rational form induced by the pencil and the original form omega like this. And all the coefficients that appear here are exactly the multiple fibers, the multiple factors that appear on the fibers of the pencil Fj. So avoiding the multiple fibers of the pencil, you can compare this with the original Pfaff equation omega. This has the information also of the multiple fibers that appear in the pencil. So now, how to produce multiple points? We can answer this. So, remark. Suppose you have that your omega can be written using two different parameters, lambda f and beta x's. Okay? And let me assume that the form is irreducible. This is an hypothesis. So observe that one very basic thing is that if the collection of polynomial f is just a permutation of the collection of polynomials x's, what I say that is the Janeiro lemma implies that the parameters lambda f, is a permutation of the parameters beta x's. This is exactly the Janeiro lemma. And this, because we're considering the quotient by the action of the symmetric groups, needs to be the same. This is Janeiro's lemma. So, if in fact lambda f is different from beta x's, if this happens, then the product of all the polynomials fi needs to be different from the product of all the polynomials xj. And in fact, it's very easy to prove that R equals to f over g is a rational first integral. It's a rational first integral. This is because this and this are integrating factors of the form. I mean, d omega over if equals to 0, and then d omega over g equals to 0. Using this, it's very easy to compute that it's a rational first integral. Okay, so second lemma of Janeiro. How are the logarithmic forms that admit an integrating factor? If omega 0 can be written using coefficients lambda f, and this is assumed to be irreducible. If you have a logarithmic form which is irreducible, so if this admits an integrating factor, admits a rational, integrating factor, not rational first integral, then the coefficients lambda I are very particular. You can select every coefficient as integer numbers. Are all integers different from 0? Up to a multiplication by some constant, all the coefficients can be considered as integers. here it's important the condition of being irreducible. Okay? So, remark, if omega 0 equals to rho lambda f, it's a multiple point, it's an L multiple point, with multiplicity at least 2, we can assume that, the first j coefficients lambda are all positive, integers and positive, and the others are all integers and negative. And it appears a very natural rational first integral of the form, the following. We can consider. We can consider f plus to be the product of all the fi's to the power lambda I, and f minus equals to the product of all the fi's to the product of minus lambda I. And in that case, R equals to f plus over f minus. It's a rational first integral of omega 0. Maybe different from the one that you can produce here. It's a more efficient rational first integral in some sense. And another very interesting computation is that if you compute this, this equals to the product of all the fi to the power lambda I to the module of the powers lambda I times omega 0. This is in some sense, the multiple fibers that appear in the pencil. So in summary, what happens? If you have a multiple point, something logarithmic in the intersection with the irreducible ones, an L multiple point, you have a pencil P given by f plus if minus with the following properties. You can associate to every multiple point a pencil of hypersurfaces on Pn, okay? With the following properties. The following interesting properties. The first one is that it has no fixed components. Why? Because the form being irreducible implies that all the fi are all distinct irreducible polynomials. So these things that appear here has no common components. So the pencil has no fixed components. B, and maybe the more interested one, this pencil has at least 2 completely reducible fibers as a product of linear forms. I mean, this and this. This is the composition of 2 fibers of the pencil as a product of linear forms. These are called completely reducible fibers. It has at least 2, f plus and f minus. C, the pencil has has multiple factors on the fibers f plus and f minus. So in the 0 and infinite fiber of the pencil. Only this and this could have multiple factors. Why? Because of this count. This implies this. Because the theorem says that the multiple fibers of the pencil needs to appear here. So these are the unique multiple fibers of the pencil. So these are exactly the fibers in f plus and f minus. So the pencil has only multiple factors on these 2 fibers and no more. And even so, the degree of the pencil is exactly, well, the degree of F plus, which is equal to the sum of the lambda I, which are positive. So do I have 5 minutes or 10 or no more? Okay, so 5? Okay. So let me also say that, so something that is a lemma, I'm going to add here. If the greatest common divisor between the coefficients lambda I is equal to 1, you can always assume that because you can divide everything, all the lambda i's by a natural number. This is well defined in the parameter space, so you can assume that. The pencil is irreducible. So I mean, the generic fiber of the pencil is an irreducible thing. But this is a consequence of Bertini theorem and some counts, okay? It's not so easy to prove that it's irreducible. Okay, so theorem. Let me finish with this. Theorem. So, I don't know, let me write in this. If omega 0 here, like this, is an L multiple point with multiplicity, well, it's an L multiple point where all the lambda 1 to lambda j are integers, positive numbers. Lambda j plus 1 to lambda d are all integers, negative numbers. The greatest common divisor of the lambda i's equals to 1. And the pencil F plus, F minus has K completely reducible fibers. Then, if all the multiplicities, all the lambda i's are 1s or minus 1s, the multiplicity is exactly K choose 2. If the positive ones have at least some multiplicity, one of the lambdas are greater than 1, and the others no, the multiplicity is K minus 1. And 3, if there are multiplicities or multiple factors in F plus and F minus, then the multiplicity is 1. This is an immediate consequence of this condition, because only F plus and F minus can have multiple factors. So if you have another description in another coefficients, this produces the same irreducible pencil here, and the fibers and the polynomials that you select here are different fibers of the same pencil. So this is an immediate consequence of this. It's not so hard to prove this. So there is a correspondence between multiple points and pencils of hypersurfaces on Pn with at least 3 completely reducible fibers. So let me say in the air what is known about this. A pencil could not have too much of these fibers. It was a first result of Georgi and Shubinski, and then improved by Shubinski. A pencil could have only 2, 3, well, obviously 2, but it only could have 3 or 4 completely reducible fibers. With 3, there are modules, there are a lot of examples to produce. But with 4 completely reducible fibers, there is only one example, which is a Hesse pencil, and it's a conjecture. It's a pencil generated by a cubic, and it's Hessian. And the conjecture is that this is a unique pencil that have 4 completely reduced fibers. And all of these things produce examples of multiple points in the logarithmic variety. Sorry for the time. Thanks.